Good morning, good afternoon, or good evening, wherever you may be, and whether you're watching live or archived. And welcome to episode number 79 in the Nautel TTT Transmission Talk Tuesday webinar series. I got that all out without looking to the side at the number. Oh, check. Yep, perfect. I'm Jeff Welton. We're going to talk about some interesting stuff today. A lot of folks seen some of our boxes, know the instrumentation on them. A lot of folks working with test gear over the years have seen some of this instrumentation in other places. So this month we're going to do test equipment month basically. And today we're going to talk about Smith charts and MER and what do they mean and what can we learn from them. As always, I found somebody smarter than me to talk about this stuff because nobody should have to listen to me ramble on about something for an hour like that. And this week we've got the handsome, the talented Mr. Stephen Lockwood. I told Steve I was going to make up a middle name for him, but we'll skip on that. So Stephen, welcome and thanks for being here.
Well, thank you. Happy to be here.
Now, you notice he's got the professional mic and I've just got the cheap Plantronics headset, so we know who the real radio guy is here.
And I have the collection of microphones that I stole from radio stations behind me. So
acquired, retrieved, recovered.
Well, back in my youth, they were surplus.
Yeah, that's it exactly. So before we get started, we've got the mandatory housekeeping stuff and we'll run into that. The cool thing, by the way, we kind of broke a record for registration, so no pressure, Stephen, but I think you've got some interest here. We're going to be relying on you to I don't know what the word is here, but we'll have some fun anyway. Okay, so the mandatory stuff. You got a little control panel. In that little control panel, you got a place to type questions, comments, criticisms, concerns, sarcasm, snark, any or all of the above. John Antonook's already mentioned that it's minus 15. That would be Fahrenheit. Not that it matters when the first number is negative, or when the first digit is the minus sign, it's just too darn cold. So John, welcome from the whole opposite side of the continent. But yeah, it's frosty there. So you can type your questions in there, hit send. I see I forgot to pull that FedEx or UPS tracking number that's highlighted on there. Somebody can see if my package is being delivered. But it'll pop up on my screen and we will see if we can answer it. John does mention that they haven't spotted any balloons there today. So fingers crossed, man, fingers crossed. You never know what could be up there though. By the way, if you're an SBE member, and I'm not sure about this particular exchange, but the rest of the webinar will qualify for half of a recertification credit under category I of the SBE research schedule. Just got my recertification. You know, I've been mentioned that I had to do it. Just got the letter that's saying my certification was approved last week, I think. Thanks, Megan. And we're good to go for another 4 or 5 years. 5 years, right? Stephen's like, I don't know.
5 years, yes. But you're old enough now that you ought to be able to qualify for life certification.
Oh, shush. I'm not that. And my problem is I was late to the party, so it took me till.
Well, you just got to get people to lie for you, and I'll lie for you.
Oh, there you go. So, and by the way, this would be the time to mention we are recording this, so if you want to catch it later on the archive, have some fun. William mentions certifiable, and he's not wrong there. My significant other may have made a comment to that effect when I got the letter the other day. So on the same token, if you've got a microphone and you're not shy and you feel like taking the risk of me not ridiculing you in public, then feel free to hit your little hand wavy icon. We'll unmute you and make you part of the conversation. So let's see, Elaine wants to know if I counted my own sessions for recertification. You know, kind of, because there is a category for presentations you've done as opposed to ones you've attended. So yeah, I guess sort of some of them. But on that, I didn't count them in 2 categories, like not as an attendee. All right, so Smith charts, and Stephen put this up, so I'm going to let you talk to this a little bit.
Well, I always like when we look at some of the history of our tools that we use in our industry. I always like to scratch my head and look back at you know, when you hear a name attached to something, you want to know who did it, and so you know, looking at, you know, who was Philip Smith, and you know, he was back when the Smart Boys did radio stuff. So graduated '05 from Tufts College in Boston, but went to work at Bell Labs, and the amount of amazing engineering fundamental stuff that came out of Bell Labs in that period is just phenomenal. And all of the communications theory, all of the control theory, and all of those things it's just fascinating to look at. And but Mr. Smith went to work in the state of the art at the time, doing directional antennas and shortwave antennas, and and part of the issue there was, how do we get as much power to the antenna, and how do we make sure that we're irradiating all of the power we can. And so that was one of his tasks that he worked on. So working through transmission lines and then the impedance matching. And it was clear to him that they needed to have a graphical calculator to do this. And so this is a time of slide rules and lookup tables, and calculations were expensive. And you remember seeing the movie about the Significant Figures was, I guess, the name of that movie, about the ladies who did all the calculation for NASA. That was the way antennas and all engineering was done, with real human calculators that had trig tables, and looked it up and wrote it on a real spreadsheet and passed it over to the next guy, and he did some addition and passed it over to the next guy, and he looked it up on the log table. And so you had all of that. And so calculations were very expensive and very difficult to do. And so a lot of effort was spent in doing graphical calculators. And it's amazing in engineering, you go back to pretty much any discipline, whether it's control theory or whatever we had at that time, you find out that there's some graphical calculators that were done to make that process easier. So Mr. Smith first published his work in the 30s, and then one of the other interesting histories of our industry in communications is always going back to the MIT radiation lab. So during World War II, there was a great effort to increase our use of radio and particularly radar and all of the tools that Uncle Sam was using to fight the war. And so they took all the smart boys and sent them to MIT. So Tom Silliman's dad was part of that group, and there are a lot of really interesting work that was done at MIT labs, radiation labs, and if you come visit the Hatfield and Dawson library, I'll show you all of the publications and books of that Dawson's collected over the years. Anyway, his first book was published in '69, and also in the broadcast industry, there's a lot of confusion with Philip Smith and Carl Smith. Carl Smith was esteemed consulting engineer in Ohio that did some just fantastically amazing antenna work and was very well respected. But it's funny because there is actually one publication on the internet that credits Carl Smith with developing the Smith chart when it was Philip Smith. And Jeff has the next one. So.
Yeah, well, and one other thing too, I'm just while you've got Carl Smith's name up there, not to sidetrack this conversation too much, but this is how we roll. He's the guy that in 1958 wrote basically a book on optimizing directional AM antenna arrays, and that's
and
still
came up with a mechanical calculator to do it. And there's wonderful pictures in that book. And if you that's something that all AM engineers need in their library. And so. But my favorite comment about Carl Smith was in his obit in Radio World, whatever that was, 30 years ago or so, was his daughter said he never took a trip that didn't have an antenna at the end of it. so
that might be true for all of us.
Well, some of us have these problems.
It's I don't know if it's a good thing or a bad thing. Let's see. William Bowen mentions I took transmission line theory in college, and the professor was Bob Redlick from Gorman Redlick, and he preferred to do all the math rather than rely on the Smith chart. My math wasn't nearly as good, so I learned to do Smith charts from a Sam's book to pass the tests.
Yes.
And so that's kind of, now the other cool thing, and I threw this up as a blindside to Stephen earlier, but and we've had this conversation before. for almost any technology, you'll hit a point where multiple people realize a need pretty much simultaneously and will start working on a solution. And they may or may, I mean, these days with the internet, of course, they can collaborate and do this stuff in lifetime. But when you're back in the early 1900s, that wasn't so much the case. You know, you couldn't just Google who's working on how to solve complex math calculations. And so at the same time that Philip Smith was working on one, the fellow with Japanese wireless telegraph, Mitsuhashi Tosaku, I hope I didn't butcher that too badly, had published a paper on almost the exact same topic. And now when we were talking about this before, my one-liner was that the person whose name you remember is typically the guy with the best marketers. But you know, that comes back to the who invented the telephone, or what was it you mentioned, Stephen? Who flew the first airplane?
Yeah, who flew the first airplane? If you wander around the world, they don't know the Wright brothers, but they know a local person that did. And
Yep.
so there's always interesting all of that, you know, and the telephone's a great example of you know, you go. I remember visiting the Soviet Union in the early '80s and saw an exhibit about some Soviet dude who did the telephone. I thought, well, okay.
Now, see, so Mr. Disembodied Voice in the background, and shout out to Ed for making all this magic happen for us. But Ed is from a little part of the world, a small part of Nova Scotia, arguably the most important part, but Cape Breton Island. And Cape Breton Island, among other things, so Marconi had a transmitter station in Cape Breton Island, but beyond that, this fellow named Alexander Graham Bell had a summer home there. And his summer place in Bedeque is still a museum, so it's pretty cool.
Well, your part of the world is important to our discipline, and in 2001, in honor of the 100th anniversary of Marconi lying about hearing an S, I beat my way all the way to St. John's, and I was quite happy because they had actually had
so you went to Signal Hill.
Yeah, on Signal Hill, and the Ministry of Propaganda for Newfoundland and Labrador had a whole display and a brochure that they had on the ferry aiming at my demographic, which I had to write them a nice letter thanking them for pandering to weirdos. And but yes, an important part of the world.
Yeah.
So.
Now, William mentions a good book, Unlocking the Sky. And if you're into this stuff, write that down, because William has steered me several times with book references, and he hasn't sent me in the wrong direction yet. Unlocking the Sky, you're right in the note. Matter of fact, he hooked me up with one called The Victorian Internet, which talks about the evolution of telegraph and how it quite literally was internet before internet. So let's see, Aaron mentions the French likes to say Marconi stole credit for Edouard Branly's work. And yep, again, multiple people will work on stuff simultaneously. There may or may not be some plagiarism. We don't judge, we just reap the benefits, if you will.
And if you steal from more than one source, it's research.
And if you credit them, it's even better. Let's see. Elaine says I need to bring up all these books on my annual Gifts for Engineers episode. So yeah, we'll have to do that. Okay. John mentions y'all are going to, holy smokes, the question thing is flying fast and furious. Keep it up, folks. I like it when we get a lot of interaction. I typically learn more from the comments than I do from the stuff that I've put up on the screen, although I didn't create this, so I learned from that too. John mentioned he read an article recently that analyzed a Marconi transatlantic test that figures the equipment was rich in harmonics and the connection was made, but probably on HF, not medium frequency.
Yeah.
And that's possibly not incorrect. So, So back to the Smith chart, and I've had the slide up there for a bit, but yeah, it's just a picture way to do something that used to involve a whole lot of numbers and calculations.
But those of us who've paid the tuition on Smith charts also, you know, it is a quick way for us to make some analysis of an antenna system and you know, a transmission system, and 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 one of the cool things about it is it works across the whole spectrum, and it actually works in fiber optic as well. You have to think about the bits and pieces slightly different, but it's still a valid tool for that situation. So it's a graphical calculator from times when math hurt. Now with Excel, math doesn't hurt, and you can quickly do complex impedance calculations, and then also show how an antenna is performing over a bandwidth and work through that.
Right.
For most transmitters that we deal with, and certainly I think most of the things that come out of your shop have a 50 ohm spigot on them. Although I know you've made some ones that have 100 ohm spigots and 300 ohm spigots, but those are for special people in special places.
Right.
But
yeah,
we want to match the antenna to the transmitter so we can get all of the energy and have the best performance.
right. And so network analyzer is one way to do that. And you mentioned here that you've kind of broken it down into how the different, I guess, branches of the industry talk to these things.
Yes, and there are a number of ways. There's also one I left off, which is reflection coefficient, which is a little more, and then the reflection coefficient can also be in polar and rectangular coordinates, and our mathematicians like that. When you start looking into historical ways of calculating things, we see that we used to do a lot of things per unit. And that was normalizing a system to a particular issue like impedance in this case, and that gave us a quick way to do some of that math without hurting our heads. But Smith charts are what we talk about, and they come in two varieties of impedance and or admittance, which is the inverse of impedance. And then for most of us who grew up beaten on transmitters, we think of the world in VSWR terms, and so we want to talk about that. And what was fun, we've done some work on old Soviet antenna systems, and the Soviets talked about running wave ratio, and on their transmitters they had a meter that presented running wave ratio, and you kind of go, well, I guess you could do it that way. And then, of course, if we start looking at our friends in the two-way world, they talk more about return loss when they measure antennas, and then
Sure.
microwave engineers also talk about return loss. And we've got a quick little chart there just to compare those. So if we look at the Smith chart impedance, a 50 ohm with no reactance, that's a VSWR of 1:1. And then a return loss greater than, well, actually, minus infinity. And
Right.
if you're exactly matched, and then we have other impedances there that show the analog for those calculations. So.
And these are good things to just tuck away in the back of your head, because some of it will apply to other things beyond this. And we'll touch on some of them in a bit. Shane has asked in the questions, he's like, so how did we land on 50 ohms as the standard for transmission systems? And I like to think it's simple as the characteristic impedance of the plumbing pipe they used.
Yes, yeah. The standard the stories that I've heard is the standard pipe sizes in the U.S. If you use those, you ended up with 51.5 ohm transmission line. And if you look at trying to find the appropriate impedance for loss versus looking at all the parameters of it, the ideal transmission line would probably be around 66 ohms impedance. But there's a lot of things that when you look at it, and I got my blood results back from the doctor the other day, and there was one of the things, I forget what it was, and the limit was 10. And I thought, well, is the limit really 10, or is the limit 10 because you have 10 fingers? If you'd have lost your index finger in shop class in 7th grade, the limit would be 9.
Limit now be 9.
Yeah,
well, and that's like, got my blood work back a little bit ago, and the doctor said your good cholesterol is good, and I said great, and she goes, no, your bad cholesterol is so bad that the good cholesterol is irrelevant. And it's okay, on to the statins we go. So
Yes.
yeah, like you say, it is kind of all relative.
So
John,
you too chose the wrong parents.
yeah, apparently so. Or the wrong diet, or the wrong lifestyle, or the wrong career, or you just throw it all together.
Yeah.
Um, Throw it all together, stick it in an airplane, and see if it ends up in an antenna.
But what's interesting, and my transmission line friends can fill me in on this, and this is something I heard years ago, was that when they decided to move towards 50 ohm transmission line, they had to change some of the sizes a bit, and I think the way I understand it now, that it's for rigid line, there's only one copper mill on the planet that makes the sizes that give you 50 ohms, and it's owned by Cable Mattel, and all of the transmission line manufacturers buy their pipe from them and then take it home and solder on the appropriate flanges and put their name and mark on it. But and if that's different, I need to be abused of the appropriate answer. But it is one of those questions of when you start thinking about who makes this stuff, and it's like dealing with Steve Lampin at Belden, and you're talking about Monster Cable, and he got this knowing look on his face and goes, they don't have a mill. And I go, well, they're using your wire, right? Yeah. But in any case, it's one of those things that I think that largely we ended up with 50 ohm because we have 5 fingers. And
so again, it came back to the marketing.
Yeah. And and this area. But just a quick review of looking at reactants. And so we have capacitive reactants, inductive reactants, and you think about I don't know how many of you had various classes, but you can calculate those from the capacitance in farads and inductance in henries. And then this along with the resistance gives us a complex impedance with a resistance and a reactance. And for mathematical purposes, we use the imaginative operator of minus, the square root of -1, which is minus j. In engineering terms, the mathematicians use -I, and was a nice time to put a footnote. In the Hatfield and Dawson library, we have a book that is the mathematician's apology for complex numbers.
And oh, by the way, side note for anybody who's interested in watching, when we get to the end, I will throw a link up on the screen for the download section of the Hatfield and Dawson website, because there's an amazing amount of resources back there by somebody, well, several people, including somebody who looks handsome and intelligent like you.
Well, and Brother Hatfield and Brother Dawson have published quite a lot, and then we've got a number of other things from some of our other co-conspirators. Have a lot of Rackley stuff on there, and other random stuff, and it's in our generic ground system drawing, it's always fun to wander around the world and have somebody that pulls it out and hands it to you, and they've been using it. So there's anyway, there's some resources there, and it's there for you to use. So
the other thing about 2 pi FL, and I'm just picking inductors in specific, because you can calculate the inductance just by the diameter of the wind and the number of turns too. So you can break it down even further than that if you need to.
Yes, and one of the fun things of looking at some of the older textbooks, and there's one that I recommend. They printed thousands and thousands of them during World War II, and it's Terman, his handbook for radio engineers, and they gave it to all of the radio guys in the armed forces for them to sit down and do that. But it has a lot of stuff that's interesting, but we're no longer rolling our own bits and pieces. But it does have a nice section on how to make inductors and how to make a good guess on as you roll tubing and all of that for your diameter and all of that. So it's got some wonderful empirically based formulas in it, and it's also just a wonderful resource when it comes to trying to work through and think about some of these items, and you still see those in bookstores, and they're fairly inexpensive still there out there. So, but in any case, we're back to the question of complex math, and so we're trying to figure out how to adjust this stuff easily and to display it in a useful manner. So
Right.
let's go to the next slide.
Well, we're getting there. But so one of the things I discovered too, and I'm ashamed to say that I'm not sure whether I didn't have enough coffee in me, or perhaps I had a little too much blood in my alcohol system at the time. But I realized, I think the third or fourth time through when I was creating or massaging your slide deck, that you gave us a step-by-step on how to do that, or how to use it. And I think that's where we're headed next, if I'm not mistaken, in a couple of slides.
So just a quick look at what we're graphing here, and there's some really cool stuff about the Smith chart. We're not going to go into all of it because it itself can consume your life. It's just a really cool thing, if I may say so. So if we look at the points on the Smith chart along the x-axis, the horizontal axis, on the right side we have open circuit. So if we have an impedance that is infinity, essentially an open circuit, that's on the right side, and a short circuit is on the left side. And then the resistance of 50 ohms and no reactance is dead middle of the chart. Now, pausing here briefly, this is a 50 ohm chart. If you work in shortwave, which I do, you may have a 300 ohm chart where the characteristics impedance of the chart is a 300 ohm system. So you're going to normalize the whole set of calculations for that 300 ohm load. So, but for most of our purposes, a 50 ohm Smith chart is perfectly wonderful and does the math. So
I'm going to interrupt real quick. Joel in the comments mentioned that the 50 ohms was also a compromise between maximum power handling, which happened at about 30 ohms, and minimum attenuation at about 75.
Right.
And mentioned also that when you've got a situation where you've got more than enough power handling but want to minimize attenuation, like in 9-inch line for UHF TV, then you're probably going to 75 ohms.
Right, and if you trade off those two parameters with power handling and attenuation, you end up with the ideal transmission line at a place where you can't buy it, and you have to make your own.
And that comes back to the 51.5 that you were talking about before.
Right. Yeah,
so,
and RCA sold 51.5 ohm transmission line up until the mid 50s or more or later. So, but anyway, so back to the chart here on the upper side of the chart, we have inductive reactance, and on the lower side of the chart, we have capacitive reactance, and I have missed a negative sign on that lower section there. It should be minus JX, and of course my daughter, who's in 8th grade, who I helped with algebra last night, would just smack me on the head because I dropped the negative sign probably 3 times yesterday evening helping her through her math.
I'd like to say that I caught that and left it there on purpose, but I'd be lying.
Yeah, well, okay. So we haven't quite crashed the Mars rover, but we went into the wrong side of the chart. So next, this is one out of one of Ron Rackley's situation. This shows the rotation of the transmission line. So as you move around the outside of it, you can rotate, and you want to go clockwise to the generator. And this is very helpful when you're looking at impedances that are transforming through a transmission line, and we have a known length of transmission line. And that's very useful.
And this was probably the hardest thing for me to wrap my head around, because I grew up on high school geometry where a circle's got 360 degrees.
Yes.
Now you're showing me a circle and telling me it's got 180.
Right, but it's a different kind of degree. So,
That's like that whole Fahrenheit Celsius thing, but we won't get into that.
well, indeed, and working with a lot of real electrical engineers that do power, when I talk about electrical degrees on things, I always have to write it all out so they understand it, and they still are scratching their heads because they're thinking about phasing of three-phase power. But the other thing that you can get from just a visual inspection of the Smith chart is VSWR information. And VSWR information is nicely contained in concentric circles around the center of the chart, and which is telling us how far we are from the ideal impedance of the system. This chart also has rectangular reflection coefficients, so you can see that reflection coefficient are between -1 and +1, and we have the imaginary side and the real side, and so you can do those in X and Y coordinates, which is actually pretty handy when you're using Excel, but that's another issue there. And you also have reflection coefficient that's done in angles, and you often see some of the TV guys use this in some of their Smith charts or their impedance charts, and where you have the magnitude and then the angle of it, and that's another way of displaying that. So anyway, those are a useful thing there.
One practical application to this too, for anybody who is setting up an HD AM, for example, the spec is 1.4 to 1 or better out to plus and minus 15 kilohertz from carrier. So if you've got a sweep right off the bat, if it's not contained in that 1.4 circle, you've got some work to do.
Exactly. And it's, that's something you can quickly know. And with the use of network analyzers in AM now, which we've been doing the last 20 years, before that, it was difficult to do that. And perhaps I can come back some point and give you the discussion of how to use network analyzers in AM. Brother Rackley's work in that was really quite helpful and changed my life, and a very useful issue. But you can look at that. And if you're setting up HD AM stuff, that's useful. And this is an example of just a quick run through of this. So this is KDLG in lovely Dillingham, Alaska, which is, I think that's roughly a quarter wave tower, if I remember properly. But we went up there, and this was a project where we were putting HD because we had money from Corporation for Public Broadcasting, so we put HD in all the villages in Alaska, and then realized that no one had a receiver. But it still got a chance for them to replace pretty much everything from the microphone to the tower with CPB grants and a lot of these facilities. That was very, very useful and a very helpful thing for them to do. But this was part of that project. So if we start at the antenna, so on the upper right, you can see that we measured the antenna with the network analyzer, and you can see that on carrier the antenna impedance was 37 ohms plus 63. And so on the Smith chart on the right, if we plot that out, and do I have a mouse? Well, you can put a mouse on there, maybe not, but you can see that over the bandwidth, if we plot that out, we get a line of points in that upper side of the Smith chart, and so trying to use so you can see that each one of those dots represents the impedance at the frequencies that we swept. So we did plus or minus 15 kilohertz from the carrier, and so that gives us a place to start. And what we want to do with an antenna tuning unit like this is match that back to the transmitter to 50 ohms, and then also with this one, the design was for an XR12 transmitter, and we knew what the phase rotation and the output of that was. So we wanted a Smith chart that was sort of looked like the Smith chart on the left. Now the chart on the left,
what Gray Hardig calls drunken smiley face.
Yeah, drunken smiley face. Yes, absolutely. And if you look at the one on the left, you will notice that that is a zoom of the in of the Smith chart, because we've so I think that's half scale, or maybe maybe 1/3 scale. But I should look. I should have told you that. But anyway, moving to the next slide, we can one of the
Side note, yeah.
yeah,
Here, I'll
side
get
note
back to
here
that one.
is trying to find a video game of a Smith chart. And so this out of all of them I've played with, and there's probably an infinite number of these out there. You start digging around, you find that lots of folks have done this. I haven't played much with MathCAD and MATLAB. I know that, and the public domain stuff in the MATLAB world has got some amazing, wonderful tools. I've played a little bit in that world, but generally don't have had a lot to do in that world. But learning MATLAB is a life goal for me, and I have yet to do that. But our newly minted engineers live in that world, and it's some cool stuff. But anyway, Herr Dr. Professor Delspreger has made this wonderful program. You can download it free. It'll do 5 points, and if you pay is $67, you can do more. And it's been, out of all of them I've played with, it's the one I like the best. And also
good.
it comes in 5 languages. So if you need more languages, and so
Quentin and Jake both said SimSmith, SIMSMITH. Is a handy Java app that free and awesome. So yep,
I'll have to look into that. That's some helpful intel.
Exactly. One other note in here, let's see. So back to the IBOC spec, the 1.4 across plus minus 15 kilohertz. Somebody mentioned not going to happen on my 4-tower inline directional. And I'll qualify that a little, because I saw one in North Houston on a 4-tower dogleg where it was so flat that with times 10 magnification on the network analyzer, you could just barely see a dot on the 430 kilohertz.
I have a picture later on of a 6-tower inline Shreveport KEEL that was done. The key is doing a thoughtful phaser design with consideration for bandwidth in it. And the one in Shreveport was done by Jack Mulaney Sr. And if you, when speaking of old textbooks, it makes the page 187 in Laporte's antenna handbook. So it's a historical sacred place, but that matching that Jack did on that, with the tools he had at the time, was pretty amazing. Both Phase Tech and Kentronic can design antenna systems that can be reasonably flat and do that. Now the question is, that's jacking up a 5-tower array and starting over. It's another phrase comes to mind of Dawson's father, who was a civil engineer, who had a phrase who said, "Any idiot can build a bridge. You just got to fill the gully full of money." And so if you want to have a perfect medium wave antenna system, we can do that, but you need to get the checkbook out.
Well, and that comes back to I ran into a 6-tower parallelogram once, where they were measuring, I was like 6.9 on the upper sideband and 5 point something on the lower. And Ron Rackley said, he goes, "I can make this do HD. We just take that tower down, move those 2 towers 100 feet over there, put another tower up over there, throw $1 million at a piece of cake." How bad do you want it?
Yeah,
so like you said, you can build a bridge, just fill the gully with money. Ray mentions, don't forget about antenna impedance matching from Karen, ARRL publication, best tutorial using Smith charts I've seen. And there was another comment from Ray's. Let me get up there. There it is. Winsmith is the best Smith chart app he's ever found. It was about $50 from Artex several years ago. Not sure it's available now.
Yeah, so I had a copy of that, and it was helpful. Yeah.
Okay.
Yeah.
All right, moving
So,
on. And by the way, we're pushing quarter to the top of the hour. In case you haven't guessed, we haven't even looked at MER. We're going to be late, but bear with us, or we'll archive it if you have to leave at the top of the hour.
okay, so
Here.
we're going to just run through this real quickly. So this is what the antenna looks like. Next one. Now, next
Now we
slide.
look at the components.
Yeah, look, now we're gonna add the components in one at a time. So first thing we're gonna do is put the inductor in. So next slide.
Okay, and you can see there, I need to get the pointer. Oh,
Yeah.
for
So
this.
that moves the point on the chart over to the right. And graphically there's a way you can add that inductor in with your compass and your straight edge. And
Yep.
now that moves the impedance there. Now next one.
Then we got a capacitor.
Yeah. So
And we go, of course, negative for a capacitor.
Yep. And that moves us down there. Okay. And then our next component is a shunt inductor.
Back to the positive.
Add to that shunt inductor. And you'll
now
notice.
Go ahead.
Yeah, you'll notice that line that it stops on is the resistive 50 ohm line. So you can see the label down on the bottom of that. But it's close to that. Yeah.
This may be a dumb question, but I'm not known for asking any other kind. On everything else, you're curving to the left. Why are you curving to the right this way?
Because it's a inductor.
Okay.
Yeah, and that would take another discussion of how the chart's laid out, and we don't have time for that today. So next.
And then another capacitor or series cap.
Yep, another series cap, and that brings us back the other direction. Along that 50 ohm line, because the capacitor is reactive,
right.
but not resistive. So yeah, so it lays on that ohm, and then now we got another component that we put in, which is a series inductor, which takes us back to the 50 ohm center chart.
Right.
And then our next step is to broadband it. So this software has nice broadbanding characteristics. So it'll calculate those other side bands, moving them through that same impedance, and show us what they do. And so next slide there, and you'll see that our little curve there on the left, and you can see that curve is centered around the center of the chart, reasonably symmetrical. I didn't calculate its symmetry. When doing for IBOC, the first 5 kilohertz points have to be symmetrical about the center axis within a VSWR spec of 1.035 to 1, and when normalized to each other. So if you're doing IBOC, we need to talk a little bit, but and we can maybe talk more about that as well. So next slide.
I'm going to pause you for a second for the questions coming in. So are 5th order filter systems required for broadbanding the system? First question.
Not necessarily.
Okay.
I think that's going back and looking at where you are in the Smith chart and how divergent things are, and then what you need to do to bring those impedances back towards your desirable characteristics.
So let's see. So Eric asks, why place the series L first before the C? The L moved the impedance into a higher Q range. If one did the C first and backed up with the L, one would stay in lower Q.
Yeah, I think that we swap them around in medium wave with not a lot of consideration for that at that location, and largely that has to do with when we actually build ATUs. It has to do with real estate and in the box and how you mount stuff. So right. Those are often interchangeable. So
and a lot of it too comes back to what you need to accomplish with it. An example, of course, in one of our infinite side route hustles, we build low frequency and medium wave navigational beacons, 190 to 530 kilohertz. And
Low
those
frequencies that cleave to the breast of Mother
things that so we'll build these things, and typically for a nav beacon, the antenna, the big goal with an antenna for a nav beacon is not to have something that a helicopter can run into. Apparently helicopters and antennas don't play well together. So a lot of it's done with a 45-foot or a 75-foot whip, like a Valcom whip, or a helipad antenna, which is just a long piece of wire strung around the helideck. The challenge with a whip is typically resonant at about 5 megahertz. And when you're at 190 kilohertz, that makes for a pretty high Q system, which means a very narrow bandwidth, but we're only broadcasting a 1 kilohertz tone, so who cares, right? Whereas with this, we need audio, we need more bandwidth, or if we're throwing HD carriers on, we need more bandwidth again. So what do they say? Know your audience, really, I guess. But again, you're not going to invest millions of dollars lowering the Q and broadbanding a system that's working within the realm of what you need, I assume.
Right, and then looking at that same example, you've got short band antennas, and even if you had at 100 kilohertz, even if you had something that was 300 feet tall, it's still going to be a short band antenna, and electrically it's going to be a short band antenna. So when you start looking at those antennas, there's a whole nother set of electrically small antennas, and there's a number of textbooks that we can point you to in that discussion. But that's a whole nother art, and you're once again worried very much about what kind of bandwidth you have, and there are a number of those antennas, especially in the LF world that actually, if you're using FSK on it, have a different tuning system for the space and the mark, because the antenna has such poor bandwidth that a short distance away in frequency, it behaves entirely different. But in any case.
William mentions, I thought much of the reason for having an inductor in series with a capacitor in a T or pi network was because variable inductors are cheap, and the inductors then adjusted to wash out the capacitance. And
that's exactly.
Yeah. And the other thing that I'll throw in there is some manufacturers, and we're one of them, like to see a series capacitor just for lightning protection, because you get a DC block that way. And then you can force some of the charge to ground through your static drain choke that we hope you have.
And you have a more reliable fuse.
Yeah, well, that's exactly right. I mean, or a less expensive fuse than the transmitter.
Yes.
So it's all about how much money you want to spend fixing it, I guess.
Yeah.
So I'm going to throw one at you, and this hadn't come up in the conversation at all. So this is totally blindside, and you can choose to pass, and I won't feel offended. What's your opinion on? And I just saw this on some Facebook engineering page not too long ago. The HEBA, those funnel-looking high efficiency antennas.
Some might comment on that. It's not appropriate for me to say much about it, other than I am not a true believer. And we, the Hatfield and Dawson entity, has spent an inordinate amount of time analyzing these. Dawson's been to Egypt. He's seen it in situ. We've looked at these. Ron and Ben were around to do a lot of analysis on that, and we did a lot of modeling using all sorts of reasons. And I do remember the Scotsman coming to NAB and standing up and telling me that, or telling the audience, that he had an antenna that did not obey Maxwell's equations, and and maybe I misunderstood him, but call me a fundamentalist. There's a lot of that that I just I don't quite work through, and there's a series of reasons, and we can talk more about that. But that's a cool. 10-hour discussion, but one of the things that, and your navigational antennas are a great example. You can get anything to radiate, and a set of old oil drums stacked up on a pallet will radiate. Now the question is it an efficient radiator?
Right.
And
Yeah, and that's what
does it
Jim.
have bandwidth, and is it a desirable antenna? And so I leave myself scratching my head about the whole issue. And then you have the next thing where folks say, well, yeah, because how it works with its secret sauce, it doesn't need a ground system, which also leaves me scratching my head. It's been interesting with the majority of the ones that we've known that have worked or that have been installed around the world have all been done at broadcast sites that already had ground systems. And so, it's hard for me for you to tell me that it doesn't need a ground system, but yet there's one there. And then you tell me that, well, we're not connected to that ground system. And I said, well, no, you are. You're on Mother Earth, and you are connected to that ground system. So anyway, there's a few things there. So
Right. Now, I was a curiosity, and Jim mentions that antenna efficiency and match are totally unrelated. You can match anything. And also, if you don't worry about the match, you can run any transmitter into anything.
exactly.
You're given enough playing around.
And laugh off all the mismatch and inefficiency of lost power. And yeah, that's perfectly fair.
Well, and one of my running jokes, running joke, it's not a running joke up in this neck of the woods. When I've got a nice inch of radial ice built up on my FM antennas, I just drop power to 75 watts because I can run 75 watts into a coat hanger. How far is it going to go? Not very, but as long as it's covering my town, then the rest is irrelevant. So again, looking at the requirement versus getting something on air. Yeah. All right, so I'll let you move on now.
This is just an example of a real antenna system, and I think this was a diplexed system, and I forget where this is, but if you look at it, you've got some of the filter characteristics, but someone's broadbanded this, trying to get that into a more acceptable load, and so they actually tied it into a knot. Now some amplifiers like that. Some amplifiers don't, and it can be good, it can be bad. So anyway, that's just an example.
I'm going to say that's the sweep I like to refer to as tornado in a cornfield, which is not really technically accurate because any tornado I've seen going through a cornfield usually goes pretty straight. But
yes, yeah. Well, and that one looks remarkably like a fish. This is the reprint version of Philip's book. Currently at $180 on eBay. They sold these at the NAB store up until maybe 10 years ago, and I know SBE sold them. This is, if you want the graduate course in this, work your way through this book, and it comes complete with the Mylar overlays in the back that you can go to the copy machine and make your own wonderful Smith charts but it walks you through the derivation of it and how he drew all those circles and arcs so that things matched and worked. So it's very helpful exercise and kind of work your way through that. And I think next, was there something else there? Yes. Yeah, here's this is let's see, it's
that's KEL.
Yeah, KEEL. So this is KEEL in the non-directional mode, if I remember. And so we can see that, it's and our friends at Nautel in their Smith chart derivation here did not give us a 50 ohm Smith chart. They gave us a per unit Smith chart. Dope slap yourself, please. And so we've got to, in order to look at that for impedance, we've got to get our calculator out and multiply 1.0022 times 50, which oddly enough turns out to be 50.11, and the same way with the reactance. And so that, that's close enough. And you can see that is also zoomed in on that Smith chart pretty nicely.
Yep. So now, a little side note about that, if you're looking at it with the user interface or on the touch screen, you can tap the screen itself. But if you tap it on the ends or click on it with a mouse on the remote user interface, it will give you the normalized impedance at the sidebands or any point throughout the waveform too, just for what it's
Yeah.
worth.
Yeah, and so and you can work your, so if you want to know what the bandwidth of your system is, you can go through and plot it at the, the various frequencies off of carrier. And here's their 6-tower 5 kilowatt inline, and you can see that Brother Mullaney, made a dot out of that, and so he really worked hard on making sure that had, in fact, better bandwidth than the non-directional.
And
And
you've got it zoomed in 600%. It looks like might be
yeah,
5.
yeah. So I was quite amazed with that, and that was exciting enough for me to post it on Facebook, and
Usually I just put pictures of food and my dogs up there.
yeah. Well, it's more pictures of naked antennas, which is anyway. And then our next one is our let's see, that's another 710. It was a year I was working
Andy's KIRO just up the road from y'all.
Yeah, and so that's also, and that antenna system there was oddly enough designed by Jim Hatfield Sr. and Frank McIntosh of Macintosh amplifier fame. And it has been modified over the years with a number of filters and other things as Vashon Island has become crowded, and but still quite a remarkable match there for that one as well. So
so this is the closing slide to your Smith chart section, and then we'll move into MER real briefly.
okay.
But so I have to ask, is that your shoulder in the picture?
No, I'm not a tattoo demographic, but if I was going to get a tattoo, that would be it. And I was laughing a few years ago. We were having the IEEE Broadcast Symposium in Hartford, Connecticut, and as we were processing through that, the next show for the venue was a tattoo show, and I was trying to get some of my fellow consulting engineers to go all get matching Smith chart tattoos. They wouldn't go for it, but in any case. And then the other one's a T-shirt somebody sells that you can get that, and it's like the T-shirt Jeff gave me many years ago with the Smith chart on it. I wear it, and all I do is get blank stares, and but it's not the only thing I get blank stares about. So.
I was talking to Gary Cavell earlier about that sort of thing, and how just some people just don't understand when we start to talk about some of these things. My real bosses learn to tune out most of the conversation and just pick up on the things that sound like they're spoken in English. So that ends the Smith chart portion at the top of the hour. We're going to carry on with MER, modulation error ratio. So for anybody who's into TV or FM plus HD, you're going to want to hang around. If you're an analog AM guy, maybe less so, but hey, whatever floats your boat. So modulation error ratio, I gave away the name of the acronym, but tell me a story.
Well, it's calculating a metric that tells us how good of digital signal we're having, and so we look at the error, and then we categorize it. And this is the nice thing about this is it's a nice analog to the way we have typically thought about quality of signals, which is signal to noise. And so this is comparable to that for digital systems. Now,
one of the things that it's important to remember, and I asked somebody to explain to me what it actually is one day, and he said, well, if you think about it, I mean, if you look at at the vector plot of an analog signal, just a regular sine wave, it's just basically a point moving around the circle. And as long as the amplitude's not changing, it just makes a circle, basically. As the amplitude changes, then it moves in and out as you go around. So if you pick any particular point in time, you're going to have a dot. Well, depending on your load impedance, your antenna bandwidth, the linearity of your amplifier, and infinite other things, including which cheek you've got your tongue stuck in, and whether you had oatmeal or cereal for breakfast, that dot will land somewhere in the vicinity of where it would in an ideal system. Now, the deviation, the difference between where it does land and where it would land in that perfect system, that's the error ratio. Is that about right?
Yeah, that's a nice way to put it. Because you're looking at essentially a target for that information, and the receiver can deal with if you hit within a certain area of that target, but when you get out of it, you're going to get out of it occasionally, and the question is, how good is good? And this is a method for us to determine how good is good. So,
Yeah.
are we hitting the target most of the time? And
that's exactly. And so the rest of this is you're going to be walking in blind on this, because these are the slides I put in without telling you about them. So we'll have a little more fun. But I'm going to hit a little side note here. Joe's asked, my AUI locks up regularly. Is there an update that can correct that? The short answer is yes, but it's not released yet. The longer answer is it depends on a couple of factors: what system you've got, whether it's running an ARM processor or a single board computer, whether it's got solid state drive or a flash card. So reach out to the support folks, Joe, and ask them, because they'll look at your specific system and see if there's things that'll help. Ultimately, and I've said this so many times on this that I'm getting tired of saying it. Y'all are going to stop believing me. But Matt tells me that the VS last beta should be out imminently. I'm tired of saying imminently, but soon. And that should solve some of these issues as well. So that's a little side note. But anyway, yeah, Aaron's lies, LOL. And look, at this point, I'll be the first to say my credibility in this area is shot, and I already know this. It is what it is. But yeah, at least for the first time in recent history, the light at the end of the tunnel doesn't look like a train. So I'm going to call it a win. Let's see. Okay, Ira mentions BER, bit error rate, is the end game measurement for digital, of which MER contributes, and that's fair. We want the bits all to get there intact and not scattered, not scrambled, not distorted to the point that they can't be decoded. All right, so moving forward. So in IBOC, as I said, we get all these carriers, and they all at any instant in time are going to hit a certain point on the quadrature. Is that about right?
yes.
Cool. And so what we're looking at is how far off they are. And now let's see, Philip, and I stole this from Philip Schmidt at our office. So anything that's wrong in these ones going forward, we're going to blame Philip. I don't know if he's logged in to defend himself, but that'll make it even more fun, because he'll hear about it later and then he'll watch it and come back to me. William wants to know if this is a Philip Schmidt chart.
Sure.
Yeah. So the big thing to remember, and you'd mentioned this in your slide, was that 14 dB is the happy place. That's pretty much the spec. Is that correct?
That's my understanding.
Yeah. And so the thing that I discovered, again, I was today years old when I learned this, which tells you, I just basically, they're like, yeah, the MER's got to be good. And that's like, cool. But I never really asked what good is. So lower is typically, when I think error rate, I'm thinking, oh, lower number would be better, but that's backwards. Lower number is worse, correct?
Well, I think it depends on if you're thinking about it in percent or log ratio.
And that may be my issue.
Yeah. And so given those two choices there, and depending on who's talking about it, they use both methods. But we want a low error or a high ratio of errors to good.
Yeah. And I mean, it comes back to, I'm going to click back to the math that you provided there. It comes back to, I mean, if you look at error over signal, well, you want error to be as small as possible, signal to be as big, so that low number makes sense. But again, whether you're talking percent versus dB, because they're inverted. So yeah, thank you.
And you know, DBs once again are what engineers have chosen to use, so we can talk about big numbers without hurting our head. And it's more of one of our techniques from bygone eras when logarithms were useful tools because they were cheat ways to calculate things.
Yeah, and that's a good point. I mean, a DB typically is just a ratio of something to something else, and you know what the
I use it
somethings
for
are.
money, but accountants have trouble when you talk about money in DB, and I remind them that it's 10 log because money's power.
I'm going to say when I looked at my bank account the other day, I'm pretty sure that I was running with negative numbers there. So yeah, that's all different math. So the short answer is this is the scatter diagram or the I forget the QPSK graph, but the for an HD signal, the ideal, the tighter you get to 4 dots on the screen, one in each quadrature, the better you're doing. The more you spread it out, the worse the MER is. And the DTV folks will have more experience with this than I do probably, but that translates very literally to range coverage.
Yeah, and when you put a noise in the system, and you know the noise, whether it's atmospheric noise or you know propagation problems or bad antenna problems or all of the things that we can beat up the signal with, you know, we take something that looks like what we have on the left, and the universe does what we have on the right to it, and you can see that you know what was a nice tight choked shotgun pattern turned into something that did not have a joke on it.
Open choke at 50 feet. Yep.
Yeah.
Like I tell the wife, you don't have to be accurate with a shotgun. You just have to be in the right general direction.
But you know, continuing that analogy is, you know, where's the bird? And 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 at one point, you know, you start looking at the information that's outside of where the bird is, and that is the air information, the stuff that misses the target.
Yep. And that's ultimately what we're looking at here. The difference between really good and really not good is not as huge as you might think. And so, you know, 56 dB hertz is about where you're going to lose reception. So that's, you know, that's the display you don't want to see. No, sorry, 0.22 dB loss in coverage. Well, you know, a loss in coverage is a loss in coverage, but it's a good point. They did do a chart about this, and not sure. I think that was your counterparts over on the East Coast, Cavell Mertz and Associates.
Yes.
That, in conjunction with NPR Labs or NAB Labs, did a lot of these coverage things. And this is where I say I drew the parallel that lower number on MER is not necessarily better because it's a bigger reduction in coverage. So again, looking at dB versus percent. But this is the thing that, because I say every, we do it, and I know Gates Air does it. I don't know about anybody else, but we provide MER instrumentation on the transmitters. And this is the kind of thing that, like, if you look on ours, you'll see something that looks exactly like that constellation. And you can go beyond that and select any specific carrier. The only reason that might be beneficial is if you got a situation. I'm going to flick back. I'm going to jump back and forth a little here because instead of putting in several slides, I put in very few slides, but just didn't repeat them. If you're in a situation where you can or dropped from, say, MP3 to MP1 or MP11 to MP3, then sometimes shutting off the extra carriers, if you discover where you're having the issue, then that may make a difference. Or you may see that it's happening on one sideband and not the other. And that might be an argument for asymmetry. So those are the kind of things that the graph will tell you. And when you first look at it, if it's scattered way out without knowing which specific carriers are, as you said, out of the target range or off the bird, so to speak, then it's easier to have the bigger picture. So correct me if I'm wrong and jump in to elucidate on any of this.
Well, and that's, that's my understanding of working through this, but when one is trying to figure out what, where you're damaging the signal and trying to optimize these issues, whether it's the phase rotation in an IBOC AM transmitter, in the matching system or all of that. One of the things I've always wanted in this was a reference receiver that had, that showed me how things were being received and how good was it when I received it. And, so I can actually be in the near field of the antenna system and say, hey, it's good leaving here. The problem's on your end. Where, with the digital systems, if we have, a bandwidth limited system, which all AM antennas are bandwidth compromised by their very nature of wavelength versus what we got to work with. You look at that, and same with FM antennas. But that question, have I beat the signal up so badly and especially on diplex systems and basic antenna design, have I beat the system, beat up the signal so badly getting through the antenna system that it's never going to be recoverable? And so those are some things that you have to look at. But yeah, that's your next challenge, is to get us a receiver with a little meter that tells us.
And so there's a little side note. I was talking earlier about the two antenna systems, the 4-tower dog leg with with the sweep being a dot. And in that one, the group engineer got in his Chevy and headed south in the main lobe. And when he lost the HD signal, when it dropped out, the analog was already unintelligible.
Yes.
On the other one, the 6-tower with the 6.9 on one side band and 5 point something on the other side band, you could park your Chevy at the base of the main tower and not pick up the HD. It radiated better in the dummy load than it did in the antenna system.
Yes, and that's that's part of having that antenna system appropriately adjusted to it. And if you get analog in your digital, it doesn't go anyplace. And if you
like
get
chocolate
digital,
or peanut butter, but not as tasty.
And if you get digital in your analog, well, it sounds like frying bacon.
And so this is one of those things, and more as we add. You chuckling at my Shively on the right?
Indeed.
That is one of the 2 bays for the little community station that I play with in my infinite spare time. And we were running at 75 watts for, well, the obvious reason, because the tuning doesn't seem to be nearly as good when you drop a whole bunch of ice on it. Haven't figured out why yet. But if we had been running HD, I can pretty much guarantee the HD coverage would have been gone at that point. And that's kind of, there are a lot of things that do impact MER. And I picked 3 of the big ones here. I've had cases on the East Coast with interference-related MER, and like I said, if you call me up and tell me that your HD doesn't have the coverage you expected, now first thing I'm going to want to know is the injection level, because if it's only 20 dB down, I'm just going to tell you, yeah, well, that's what you get at that injection level. But if you got a higher injection level, then the first thing we're going to look for is what's nearby on adjacent channels, and that you can't change, other than doing an asymmetry if you're able to do that on the other first adjacent, other side band. So a lot of it can be, but again, the MER reading is a tool, and it lets you know where to look. So I like the idea you said about coming back to talk network analyzers, because we could dig into this a little further as well, but AM and FM. So
happy to do so.
Well, and these days with the HD, the difference is becoming much smaller. I mean, DTV, AM component, FM component. HD FM, AM component, FM component. HD AM, AM component, PM component, but it's still FM, whether phase or frequency doesn't matter. So, you know, the only difference now is where we put the analog signal relative to the digital ones. But let's see, is there anything else that you can think of that we've missed on this? We're drawing up, we're 15 minutes past the top. I want to respect people's days just a little bit and let them have some time, but what do you think?
I think that that gives us a quick an introduction to both topics. And one of the the things we learn about all of these topics is you quickly discover that there's people who've dedicated their whole life to just this one subject, and you find out that we have acknowledged that there's an iceberg there, but we've maybe put our ski pole in the top of the iceberg on all of these subjects, and but there are really some interesting and elegant engineering that is in all of these systems. One of the things I take a big step back when I look at all of these stuff, all of this, this digital process is don't get me started on LTE systems. I mean, LTE systems are just truly phenomenal, and it's one of those things where I want to take a step back and watch the whole process, and there the engineering in those systems and how they decide to get all the things to you that you need so you can watch people fall off of skateboards on YouTube is just phenomenal. And
now, speaking as the guy that deals with cabinet radiation complaints because they want the cabinet radiation to be 0.0000 or 1% of the spec.
I have a God-given right to operate below the background noise of the universe.
Yeah, or when you're sending a guy out with a spectrum analyzer with a 95 dB noise floor, no attenuators at all, and then trying to measure a signal 120 dB down.
Yes.
But that's a whole different discussion, and we do have a spectrum analyzer conversation coming up next week. And coincidentally, you didn't know this, Adam Middlecoop from Support is our guest, and he came to mind purely based on a conversation you and he are having at the moment about a troubleshooting job you're working on.
Uh-huh.
So Adam, so you want to log in as a guest, we'll put Adam on the hot seat. I shouldn't announce it right now, just in case anybody from tech support's logged in and gives them a heads up, but there you go. Let's see, Ray asked on my antenna why I didn't get a slant V instead of the ring because more broadband, and we do have one sitting on the shelf waiting to have the budget, and currently we got 6 inches of snow on the ground, but the budget and the time to get the other antenna installed. Feasible or possible to have some way of measuring MER as actually radiated from the antenna and apply adaptive pre-correction to minimize MER in varying icing conditions. So that depends on your manufacturer. We do have adaptive pre-correction. At least one other manufacturer has adaptive pre-correction. In our iteration, we do look at the mask clearance, which is on the spectrum analyzer, arguably probably just as critical as the MER. The two are somewhat tied together. So yeah, that is being done. It's done at the exciter end because the reflected power coming back is just as visible in the amplifier and the exciter as it is on a far field receiver. Probably more so because you're impacting my transmitter directly. But yeah, so is there an MER device out there that can work from a receiver, Stephen?
I don't know of any. I know that there have been some discussion that such animals live in the folks who bought Ubiquity, that there are some test receivers there, but I've asked about it before and I get not full disclosure. But in any case, with you're back to your adaptive pre-correction, which has been one of those things that has been really fun to watch because as various portions of your transmission systems get ugly, and Jeff has this lovely sauce that he can make inverse ugly, on the front end and put it in, and we can get beautiful coming out. And and that's just a fantastic thing to watch. And and so if to be able to do that on the fly is even more elegant. So
yeah. Let's see. Tim mentions that a certain cell provider, whose name I won't mention, but consists mostly of letters and an ampersand, wants a noise floor that is the equivalent of an ant fart in a tornado.
Why? Yes.
I need to write that down.
I should use the standard line is, some might suggest so, but I couldn't possibly comment.
Yeah. Let's see. And Joel mentions that the GV with a 6810 at a site which gets severe icing, and it will drop to half power to SWR even with radomes. And sure, because cover the radomes with ice, and you just created an antenna in a reflector. So yep, I get that. And Tim's talking about a reference site. So yep, they're going to want it even further down than the average. All right, moving on. We've kept folks 25 minutes past the top of the hour. So there are online information for everything. I did promise that I'd have the download link for the Hatfield and Dawson website. If you click back from that, you can also find a list, not linked, but a list of publications that have come from those fine folks. And there is a pile of information on that site. I may or may not have I guess if it's listed for download, me clicking download is technically not stealing, and I try not to use anything without attribution, so it wasn't even plagiarized, but it's a huge resource, and I really appreciate it.
To quote Tom Lear, do not let others work, shade your eyes.
Yeah. And what do you say? If you borrow from a bunch of people, that's research.
Absolutely. Absolutely.
So, awesome. That is so awesome. Let's see, Barry Michigan's BDR.net, and Barry does his Thursday BDR lunch, which is a bunch of folks talking about various topics of interest. This archive will be, or this webinar will be archived. You can find it on our YouTube channel as soon as Mr. Disembodied Voice Ed Sylvester gets her done. Again, shout out to Ed for sticking with us this long. If he hasn't nodded off in the background, that's a testament to his intestinal fortitude right there. Waves newsletter, there was one out not too long ago, and that, folks, is about it. So on that note, Mr. Stephen Lockwood, I want to thank you very much for putting with us today. Go give the hounds a scratch and tell them I said thanks for letting me bore you for a while.
Well, thank you, sir, and enjoyed the time.
Thank you. And folks, thank you all very much for tuning with us today. By the way, our 54th birthday was, I forget, might have been yesterday, might have been the day before, but very, very recently. So happy birthday to us. And
Saturday the 11th, my friend. Saturday the 11th.
Thanks. See, this is why we keep Ed around, because he keeps me informed at all times. So on that note, thank you all very much, and we will see you next week. Have a wonderful week. Bye now.